In this presentation, we are going to look at the beta function. Now, we're going to see how we can re-express the beta function in terms of, or just re-express it essentially. Now, what motivates this is the differences between the beta 1 distribution and the beta type 2 distribution, the beta prime distribution as it's also known. The key thing arises when we're looking at the probability density functions here. So I'm just going to scroll down here a little bit so you can get a closer look. So here we have beta 1, okay, down here we have beta 2. So the key thing arises here, okay, when we're talking about the support, the range of values that they are defined for. So in the case of the beta 1 distribution, it's 0 to 1, but in the case of the beta 2 distribution, it's 0 to infinity. Now they have different applications where 0 to 1 and 0 to infinity would make sense, and that's fine, but it's just a case of what do we do when we're trying to use calculations derived from the probability density function, calculate the mean and variance and so on. Okay, so in the first instance, the beta function, as well as being expressed in terms of component gamma functions, the conventional expression of it is in terms of an integral from 0 to 1 of x to the power of alpha minus 1 times 1 minus x to the power of lambda minus 1 dx. Okay, now this is the alternative expression of it. Now the point of this video is based on this, how do you get to this? Okay, that's just the point of it really. Okay, so the key thing here is we're going to use a change of variable approach. Okay, so I'm going to start off with t. Okay, let's just look at, I'm going to sort of, well, x actually, but let's just rewrite it out again. I'm going to start off with my conventional gamma beta function, alpha minus 1 times 1 minus t of lambda minus 1 dt. Okay, and what I'm going to do is try and re-express that as an integral in this form here. Okay, so I'm going to start off with t, and I'm going to re-express that t as s over s plus 1. Now this is a sort of change of variable approach, and this is a sort of, how shall I put it, an educated guess. Basically, you can try out a load of these different combinations, but essentially you'll find that this one works. Okay, that's it. So we're just going to build it up. T to the power of alpha minus 1 can be expressed as s divided by s plus 1 to the power of alpha minus 1. And that can be written as s times s to the power of alpha minus 1 times s plus 1 to the power of 1 minus alpha. Okay, so essentially I'm just getting the 1 over s plus 1 is s to the power s plus 1 to the power of minus 1. Okay, that's essentially it. Okay, just don't drop the ball there. That is alpha minus 1. That is 1 minus alpha, because this is a fraction. Okay, silly mistakes there can be very costly. Okay, 1 minus t is 1 minus s over s plus 1, and that can be rewritten as 1 over s plus 1, and that is 1 plus s plus 1 to the power of minus 1. Okay, so 1 minus t to the power of lambda minus 1, that is equal to s plus 1 to the power of 1 minus lambda. Okay, we're changing the signs there, okay, because it's inversion. Let's just combine those two expressions there. We have s to the power t to the power of alpha minus 1 times 1 minus t to the power of lambda minus 1. That is equal to s to the power of alpha minus 1 times s plus 1 to the power of 1 minus alpha times s plus 1 to the power of 1 minus lambda. Okay, and just tidying that up, we get s to the power of alpha minus 1 times s plus 1 to the power of 2 minus alpha minus lambda. Okay, so what we're going to do now is calculate. So we would use dt, but we need ds. Okay, or need to express dt in terms of ds. Okay, so what we're going to do there is differentiate this expression here. Okay, get it differentiated with respect to s, and we get 1 over s plus 1 squared. All right. Now, and when we re-express that, dt is equal to s plus 1 to the power of minus 2 ds. Okay, just actually the fundamentals of differentiation just come into play here. Okay, just be ready for that. Okay, so piecing it all together, we get, this is the most of the expression here now. Okay, we have seen this so far, but what we're doing here is adding in the dt term, which in this case is s plus 1 to the power of minus 2 ds. Okay, so that 2 cancels out with that minus 2. Okay, so what we're left with is s to the power of alpha minus 1 times s plus 1 to the power of minus alpha minus lambda ds. Okay, or you can re-express it as follows there, as a fraction, which is fine as well. Now, let's get the limits. So when t is equal to s plus 1, so just actually what's the limits? The limits of integration. So in the first instance, it's f of t dt, something like that. So essentially what we want is, well, it's a function of t there, but essentially the limits are 0 and 1. So if t is equal to 0, what would that make s? Okay, necessarily s would also have to be 0. So this expression is only possible s divided by s plus 1. That if that's equal to 0, that means s is equal to 0. It's only possible if s is equal to 0. If t is equal to 1, what does that tell us about s divided by s plus 1? So s divided by s plus 1, that is sort of almost seems like a tautology, a sort of contradiction in terms, but it actually is possible if s is equal to infinity. Essentially, infinity is a funny thing. If you add anything to infinity, it's still infinity. Okay, so that's it. So that's what the new limits are. Okay, so we just piece it all together now. That is our expression there. Well, actually, in terms of dx, that's our expression there. Well, actually, sorry, I should be consistent there, but that was the original expression as above, and that can be rewritten as the integral from 0 to infinity of x to the power of alpha minus 1 times x plus 1 minus alpha minus lambda dx. I'm just going to switch that there. Okay, sorry, just I noticed here, if you're following from here, that dropped the sign, so that should be the power of alpha minus lambda, not alpha times lambda. It's just missing a sign there. Okay, just watch out for that. I just dropped that sign there, alpha plus lambda. Okay, that's it. That's how we re-express the beta function.